Hello guys, in this video I'm going to solve a problem related to partial discharge behavior. So in the given problem we have a test object as shown, and in this test object we have an air cavity as shown here, and the pressure in the air cavity is 1013 millibar, and its dimensions are 1 millimeter by 5 millimeter. Its height is 1 millimeter and width is 5 millimeter. Both the cavity and the test object, they are in cylindrical shape. Now we need to find the onset of partial discharge for the test object. Onset means inception voltage of this cavity. Okay, so first of all, we need to um, understand the geometry. So as it is given in the question that the geometry of the test object and the cavity, both of them, they are cylindrical shape. So, so this is our test object, and inside we have cavity. Cavity looks like this, and the width of the cavity is 5 millimeter, and height is 1 millimeter. So now if we draw a three capacitance model of this insulator, then it will look like this. We will have healthy insulation which is in parallel to the cavity. So we have, which can be modeled as capacitance Ca. Then we have, in parallel to that, we have cavity, and its capacitance can be labeled as Cc. So capacitance of the cavity, this one, Cc. And then in series with this cavity, we have healthy part here and we have healthy part above. Both of them can be combined as capacitance Cb. And then we have applied voltage UA. Now the voltage across the cavity can be determined using voltage division rule. So voltage across the cavity UC can be determined as UC is equal to UA multiplied by CB over CC plus CB. So that's the voltage across the cavity. Now, what are we required to determine? So we are required to determine the inception or onset voltage. And by definition, inception or onset voltage is the applied voltage required to ignite the discharge in a cavity, to break down the cavity. Okay, which means if our cavity breaks down at a voltage UCI, then the applied voltage UAI is the inception voltage, which we are required to find. Okay, so if we rearrange this equation, UAI will be equal to UCI multiplied by CC plus CB divided by CB. Okay. Now we need to determine this parameter. So we can calculate all these values, CC and CB. How can we calculate? From the graph represents the breakdown in the cavity as a function of PD, pressure multiplied by the gap distance. Okay, we know the gap distance is 1 millimeter, so or the height of the cavity, which is shown here. So height of the cavity is 1 millimeter, and the pressure in the cavity is 1013 millibar. So PD in the cavity will be equal to 1013 millibar, can be written as 1.013 bar multiplied by 1 millimeter. So this will be 1.013 bar mm. Okay. Now we need to determine this point, which is close to 1. Okay, so this is 1 bar millimeter. So we are gonna look at this point almost close to this. So which will be approximately here. Okay, so this is 1, this is 2, this is logarithmic graph, this is 3, 4, approximately 4.5. So the breakdown voltage at this point is 4.5. Breakdown voltage of what? Breakdown voltage of the cavity, because this graph shows the breakdown voltage of the cavity as a function of PD. Okay, so breakdown voltage will be 4.5 kilovolt in the cavity. Now we got UCI. So UCI is equal to 4.5 kilovolt. Now we need to determine capacitances CC and CB. For that, again, let's review the cavity. So the geometry of the cavity is like this, where the distance between the discs or between the sides of the cavity is 1 millimeter, we call it D, and then the diameter of the discs of the cavity, because this is a cylindrical shape, so the faces can be viewed as discs. So the diameter of the discs is 5 millimeter, and the radius of this disc from the center to the edge will be 5 divided by 2, so which will be 2.5 millimeter, or this is equal to 0.0025 meters. Okay, so now from the formula for the capacitance, C is equal to epsilon A by D. Okay, now for the capacitance CC, we will have, because capacitance CC is the capacitance of the cavity. So we have air, and the permittivity of air is epsilon naught, and area of the plates here, area of the parallel plates. Here we can view them. We can see these plates as our circular plates. They are not rectangular. So area of circular plates or area of discs can be determined as pi r square divided by the gap distance d. Okay, so we are going to plug the values. Epsilon naught is 8.85 into 10 raised to the power minus 12 multiplied by pi, and radius is half of the diameter, which is 0.0025, and we have square here, so we are gonna put square. Okay, and divided by d is 1 millimeter. We need to put all the dimensions in meters, so we are gonna put it 0.001 meter instead of 1 millimeter. And if we solve it using calculator, we will get a result 1.738 into 10 raised to the power minus 13 farad. Now we need to determine CB. What is CB? Let me draw the geometry again for better clarity. So we have, this is my insulator, okay, and in between I have my cavity. So this is the cavity, okay. Now the CB is actually the capacitance of the healthy part of the insulation, which is in series with the cavity. Okay, so now area will remain the same as we are determining capacitance from here to here, excluding the cavity. So area of the discs will remain the same as the area of the cavity, but now the height will be, our total height of the insulator was 3 millimeter. So this total is 3 millimeter, and height of the cavity is 1 millimeter. So what will be the height of the healthy part? That will be 3 minus. So d of b will be 3 minus 1, which will be equal to 2 millimeter. Okay, so this will be our d for the healthy part, which is in series with the cavity. So this is what we will use here. So CB will be equal to, now we will have permittivity. We will use permittivity of the resin. Okay, in the question we are not given the permittivity of the resin, but we can use, okay, it is given here, it's written here, we are given relative permittivity of the resin. Even if it is not given, you can Google it. You can easily find out the relative permittivity of the resin. So it is 4 here, relative permittivity. But in this formula, where we need to find the capacitance, we need to use the absolute permittivity. So we will use epsilon pi r squared divided by dB. So that will be equal to epsilon r multiplied by epsilon naught pi r square divided by dB. And this is equal to, epsilon r is 4, epsilon naught is 8.85 into 10 raised to the power minus 12 multiplied by pi, and radius is same as the cavity, 0.0025 whole square divided by, now dB is millimeter. So that will be 0.002 in meters. So after putting the values, we will get the value of CB as 3.477 into 10 raised to the power minus 13 farad. Okay, so now we got all the ingredients to get the value of UAI, which is the inception or onset voltage, which can be defined as the applied voltage required to ignite the discharge in a cavity. Okay, so we are gonna put the values in the above equation, which is UCI multiplied by CC plus CB divided by CB, this equation. And we have all the values. UCI is 4.4 kilovolt, 4.5 kilovolt, 4.5 multiplied by CC is 1.738 um, plus CB is 3.477. I'm not writing multiplication factor because multiplication factor at the numerator will be cancelled with the multiplication factor at the denominator, which is 10 raised to the power minus 13. So divided by 3.477. And we will get this equal to approximately 6.75 kilovolt. Okay, this is our final answer.